So we've previously discussed local extrema, and those were basically peaks and craters of the graph of a function of two variables. Well, what if we then ask, what is the highest point of a function of two variables, period? Okay, so if I give you a set and I ask for the highest point that function attains, that maximum value of the function on the set, how can we find that? How can we find the maximum value? Or how can we find the lowest value, the minimum value? That's the topic of absolute extrema, looking for the highest of highs and lowest of lows of a function, okay, on a given set. And before even attempting to answer that question, we would like to know that the highest point and the lowest point, so the minimum, the absolute minimum, and the absolute maximum, actually exist. And here the extreme value theorem will help us. So if a function is continuous on a closed, which means it includes its boundary, so the region that we're looking at inside the in the plane is closed, includes its boundary, and bounded, it's finite, doesn't extend infinitely. Well, we know if a function is continuous on such a set, it attains its absolute maximum and absolute minimum value on that set. So our work isn't in vain then, so long as we could check that a set is closed and bounded and that the function's continuous. We know that at the end of our search, we'll find the absolute max and min on that set. Now, we've dealt with this situation before with functions of one variable in previous calculus classes. So if you wanted to find the absolute extrema, you looked in two different places. Broadly speaking, you looked at the critical points, and the critical points for functions of one variable were where the derivative was zero, so the points where the slope is zero. And you also had to check one more thing, and that was the endpoints of an interval. So take a look at this function here. We want to find the absolute max and min between a and b, where a and b are included, since this is a square bracket there, so we're including the points a and b. This set is indeed closed, includes its boundary points, and bounded, doesn't extend infinitely. So you had to check the critical points. I mean, here's a critical point. There's the peak there, the derivative 0. Here's another critical point. So we have two critical points here. And you also had to check the endpoints. Notice the absolute max actually showed up at the endpoint. Okay? Even though that's not a peak there, the absolute max showed up at the boundary. The absolute min, on the other hand, shows up at a trough or a crest. Okay, so that's where the absolute min did indeed show up at a critical point. And we're only considering the interval a, b, so we don't have to worry about what's going on outside that interval. And it's important that we have a closed and bounded set there to guarantee us that we'll be able to find the absolute max or min. I mean, consider if you use 0, b instead. So going from the origin, but not including the origin, where the function isn't even defined, we get an asymptote. Notice that we're getting an asymptote here, ever closer to the y-axis, but never reaching it. So this function just keeps getting higher and higher and higher, never getting to the y-axis, and so we never get a max. That's the importance of the having a closed set there, where the function is continuous and defined on that closed and bounded set. So the lessons to learn here is that for functions of one variable, we looked for critical points in the interior of an interval, and we looked for the boundary points, endpoints. So the boundary of a interval are endpoints. Okay, so we have to check the critical points in the interior and the boundary of our interval. That's the lesson to get there. And we do something similar, broadly speaking, for functions of two variables. So if we have a set R, okay, which is in the plane, that's an analog to an interval along the line. So we have a set R in the plane. And we want to get the candidates for our absolute extrema. There are three different things we're going to look for. And they're going to be in two places. So two places, just like in for functions of one variable. The two places are the interior and the boundary, exactly like the function of one variable. So in the interior, we're going to look for critical points, same as for functions of one variable. And the critical points, I'll remind you here, are where both partial derivatives are simultaneously zero, or that one of them does not exist, which we won't be dealing with that situation. So we're only going to focus on where the partial derivatives equal zero. And we then also have to check the boundary to see if we have a situation that we saw up here, that the highest point is achieved at the boundary. And so what is the boundary of a set of that's two-dimensional? So if this was the set R, what is the boundary of that? It's going to be a line. Okay, it's going to be this line out here that bounds the set R. Okay, didn't draw it right above the blue there, just around it, but basically that blue line is the boundary. Okay, so we're going to get a function of one variable by looking at the function at the boundary. This here means the boundary of R. So if you define the function just along a line, it's going to be a function of one variable. And so that's the second category. So we're going to look at for critical points of the boundary function, which is a function of one variable, which is the function of two variables at the boundary. And the third thing we're going to look for is the endpoints of the boundary function. Okay, so if we do get a boundary, then we have to consider also the endpoints. So this problem here is analogous to the function of one variable problem. We actually do have a function of one variable, and we will have to check the endpoints of this function of one variable, where it's at the interval we're looking at. And of course here I write generally because a critical point can show up at the boundary, so we have to pay attention to that. Here I'm just speaking broadly. So what is the procedure that we'll use in order to find the absolute extrema on a closed-in bounded set or in the plane? Well, first we're going to look for the critical points. That's category 1 there. Then we're going to look at the boundary, and we're going to look for critical points of the boundary function. Here, this is the critical points of a function of one variable. Please make the distinction between critical points of the boundary functions and just general critical points of the function. Okay, and when we do an example, you'll see clearer the distinction. And then finally, once we gather these three different types of points, we then plug them into the function and compare. Okay, the greatest value will be the absolute max, and the lowest value will be the absolute min. And let's just jump right into it and see an example and see how this works. So here's our problem. We're looking for the absolute max and min of this function of two variables that you see there. And we're doing it over this triangular region. Okay. Now this triangular region includes its boundary. Okay. These inequalities are equal signs, so it includes the boundaries, the boundary, and it's finite. So it's closed and bounded. Okay. It's not extending infinitely. So what does the extreme value theorem tell us then? We're guaranteed that we're not working in vain. We will indeed find the absolute max and absolute min in this set. Okay? So on the interior, generally speaking, look for critical points. So take the partial derivative with respect to x and y, set them equal to 0. Here we get a line as a solution, the line y equals 8. And here we get another line. And what is a critical point? Where these two lines would intersect. So in other words, where the partial derivatives are simultaneously 0, you could take this 8 and plug it in here, for example, and solve for x, and you will get 4. So the critical point is 4, 8. And okay, that's a critical point. No need to try to classify it here. We're looking for the absolute extrema, so we're just going to plug in the critical points into the function and compare all the values at the points we are considering. So good. That's the critical point, and that's all the critical points there. And now let's go to the boundary. Now, what do we look for in the boundary? We look for critical points of the function at the boundary. And here, I'm just going to call the function at the boundary function, okay? That's just my terminology. It's better than saying the function at the boundary, okay? We just say boundary function. In order to find the boundary functions, we're going to have to describe the boundary, okay? Our region, if we were to draw our region, it looks like this, okay? X is between 0 and 15, and y is between 0 and the line 15 minus x. So here's the line 15 minus x. And so y needs to be below that, but greater than 0. So this indeed there is our region. Okay, and 4, 8 is in this region. So our critical point is important for finding the critical point that we found there is important for comparing all the different candidates for the absolute extrema. And if we want to find the function at the boundary, our boundary functions, well, we're going to have to parameterize the boundary curve, okay? And this region is triangular. So we're going to have to parameterize it using 3 different parameterization functions. One for C1, the other for C2, and for C3. Let's begin with C1. So C1, what's a parameterization of that? It's basically this vector function that maps onto that line. If we just use this very simple one and note that t is between 0 and 15, we're going to take that parameterization of that curve and plug it into the function. That's the meaning of this. We plug it into the function and we get minus 8t plus 160. What are you seeing there? You're seeing the value of our function of 2 variables only along C1, okay? And we stay only along C1 by making sure that we consider only the interval, 0, 15. That's where t is defined for our parameterization. Okay, so we then have G1. G1 is going to be negative 8t plus 160. What about C2? Well, we're going to parameterize it this way. So x is going to be 0 here, but y is going to have the t, and it's also going to run from 0 to 15, our t. And what do we do now? We take the parameterization R2 and plug it into the function. Okay, so here's the function up here. You just plug in, wherever you see a x, plug in a 0, and wherever you see a y, you plug in t, the y value of the parameterization. As you'll recall, this is y of t here, and this is x of t. Okay, so plugging that into the function, plugging the parameterization into the function, you get this, and that's the value of our function of 2 variables only along C2. Okay, and finally, the trickiest one of these is probably C3. Okay, and here we're going to just let x equal t. Okay, and if x equals t, Well, what does y have to be in order to stay on that line? If x equals t, y better equal 15 minus t, right? Because the boundary is 15 minus x, and if x is t, well then y better be 15 minus t. So that's going to be our y value there, you know, and we're going to let t go from 0 to 15. So you start at this point here, and you move along down to that point at 0, 15 there. Or sorry, 15, 0. So then we're going to get a function of one variable by plugging in the parameterization of the curve C3 into the function, and we get this function of one variable. Notice that all our boundary functions are functions of one variable, and they have endpoints. The endpoints being, they're defined on the interval 0, 15 for t, and so the endpoints is 0 and 15, 0, 15, and 0 and 15. Is this the only way to parameterize the curves that you see there? Absolutely not. There is infinity of ways to parameterize those curves, but we just chose the simplest one. And this would work no matter how you choose, for sufficiently well-behaved functions that we deal with, no matter how you choose the parameterization of the curve, this will still work out. And so for category 2, we're looking for critical points of our boundary function. So what do we do? This is now back to Calc 1 territory. Okay, you're talking critical points of functions of one variable. So we take the derivative of the first one, and we get -8, and that's never 0. So the function does not have a critical point on C1. Okay, a boundary critical point, C1. We take the derivative of G2, we get t equals 6. And so that means 0, 6 is a critical point of the boundary function, not the actual function, but the boundary function. Okay, and how did I get, you might be thinking, well, you only found 6 there. How did you get the 0? Well, recall that our parameterization of C2 was 0t. So t equals 6, but this x is going to be 0, and that's where that's coming from. We are dealing with the function at the second curve. What about our third function, the function at the third curve? Well, taking the derivative, setting get equal to 0, we get that t is equal to 25 fourths, 6.25. And so this is also a critical point of the boundary function G3. And you might say, how did you get this final term here? Well, again, look at the parameterization. So if t is equal to 6.25, then the x value will be 6.25, and the y value will be 15 minus 6.25. And that's what you get here. Okay, so far we've considered 1, critical points of the function of two variables, 2, critical points of the functions of one variable, okay, the boundary functions, and 3, we need to consider the endpoints of the boundary functions, or if you will, the boundary of the boundary functions. Okay, so we're going to consider the endpoints of our of the interval where our boundary function is defined. And what is that interval? It's 0 to 15 for all three of these functions. And these correspond to t equals 0 for G1 corresponds to the origin, and t equals 15, the 15 bound endpoint, it corresponds to 15, 0 for G1. Okay, that's just looking at the plugging the endpoints into our parameterization. Plugging the endpoints into our parameterization for 2, you get 0, 0, and 0, 15. And for 3, 0, 15, 15, 0. Now, it's no surprise that there are repetitions there, because look at that point there, and say this point here, and this point here. Okay. The endpoints are endpoints for different curves. So the C2 and C1 intersect at the origin, so it's an endpoint for both of them. That's why you're seeing the repetitions going on there. And now what are we going to do? We're going to take all three of the different candidate types that we found. Critical points, and on some days I've called them Calc 3 critical points to distinguish them from the second category of critical points, which is critical points of the boundary functions, or sometimes I've called them Calc 1 critical points. And number 3, the endpoints of our boundary functions. And we get all of these different points. And now what do? We take each of these points and plug it into the function. So we'll take 4, 8, for example, and plug it right back into this original function. So 4, 8 means wherever you see an x, you put a 4, and wherever you see a y, you put an 8. And if you do that, you will get 192 at the end. Do the same thing for the rest of the points. So what are these 2 points? These 2 points came from category 2, critical points of the boundary functions. And these 3 points, what are these points? Where did they come from? They came from the endpoints of the boundary function. And now we take a look at all of the values of f at all of these candidates for our absolute extrema. And we find that the highest value is 196. And so it is the absolute max on R. And the lowest value is 40. And it's the absolute min on R, found at the point 15, 0. Okay, so our critical point turned out to not be the absolute max. The absolute max occurred at the boundary, and so did the absolute min. So the boundary is definitely important to consider there. So what you see here is the function that we considered, and you could see C1 here, and our boundary function. Here you see instead of using the variable t, x is used, and also that's a typo. G1 should be 160 minus 8x, not x. C2, the boundary function, we use t instead of y, and C3. So what you see, these colors that you're seeing, the red is the boundary function at C1, and the blue is the boundary function on C2, and the orange is the boundary function at C3. And after gathering all the different types of candidates for the absolute extrema and comparing, we see here in blue that was the that was the absolute min. It occurred at the endpoint of the boundary. And we have also the absolute max, and it occurred, and it's there red. You can see it in red. And it occurred at the critical point of the boundary function. Not the critical point of the function, but the critical point of the boundary function.